In the early 19th century, the study of heat and energy was advancing rapidly. Scientists were intrigued by the nature of heat and how it interacted with matter. One of the pioneers in this field was Sadi Carnot, a French engineer and physicist. Carnot was fascinated by the steam engines of his time and sought to understand how they worked more efficiently. He began to explore the relationship between heat and work, laying the groundwork for what would become the science of thermodynamics. Carnot's investigations led him to conceptualize an idealized engine, which we now refer to as the Carnot engine. This theoretical construct was a perfect engine that operated in a cycle, transferring heat between two reservoirs and performing work in the process. Carnot's work was revolutionary because it introduced the concept of reversibility in thermodynamic processes. He proposed that the efficiency of such an engine depended solely on the temperatures of the heat reservoirs, not on the substances involved in the cycle. The next significant figure in this unfolding story was Rudolf Clausius, a German physicist who extended Carnot's ideas. Clausius was deeply influenced by Carnot's work and sought to build upon it. He introduced the concept of the transformation of heat into work, focusing on the quantitative aspects of this process. Clausius formulated a mathematical expression to describe the heat absorbed and work done by a system, emphasizing that some heat is always lost to the surroundings and cannot be fully converted into work. During his investigations, Clausius observed that heat naturally flows from a hotter body to a cooler one and not the other way around. He expressed this idea mathematically, leading to the formulation of the second law of thermodynamics. This law states that in any cyclic process, the sum of the heat added to the system must equal the sum of the work done by the system plus the heat lost to the surroundings. Clausius was the first to introduce the idea of a quantity that could measure the irreversibility of real processes, which he called equivalence value. Meanwhile, in Scotland, another key figure was making contributions to the understanding of thermodynamics. William Thomson, later known as Lord Kelvin, was also inspired by Carnot's work. Kelvin introduced the absolute temperature scale, now known as the Kelvin scale, which is essential for understanding thermodynamic processes. He collaborated with Clausius and others to further refine the principles of thermodynamics. As the study of heat and work progressed, scientists began to notice that certain processes seemed to have a preferred direction. For instance, heat flows naturally from hot objects to cold ones, and gases expand to fill available space. This observation suggested that there was a fundamental principle governing the directionality of natural processes. Ludwig Boltzmann, an Austrian physicist, provided a statistical interpretation of this principle. Boltzmann was interested in the behavior of gases at the molecular level. He proposed that the properties of gases, such as temperature and pressure, could be understood in terms of the motions and interactions of individual molecules. Boltzmann developed the kinetic theory of gases, which describes how the energy and distribution of gas molecules relate to macroscopic properties like temperature and pressure. Boltzmann's key insight was that the behavior of a large number of molecules could be described statistically. He introduced the concept of microstates, which represent the possible configurations of a system at the molecular level. Boltzmann showed that certain configurations, or microstates, were more probable than others. This led to the idea that systems tend to evolve towards configurations with the highest probability, which correspond to states of maximum disorder or randomness. To quantify this tendency towards disorder, Boltzmann introduced a mathematical function that related the number of microstates to a macroscopic quantity. This function provided a measure of the disorder or randomness of a system. Boltzmann's work was crucial in bridging the gap between the microscopic and macroscopic worlds, showing how the behavior of individual molecules could explain the thermodynamic properties of materials. The concepts developed by Carnot, Clausius, Kelvin, and Boltzmann laid the foundation for a new understanding of heat and energy. Their collective work revealed that natural processes have a preferred direction, governed by a tendency towards greater disorder. This insight has profound implications for a wide range of phenomena, from the behavior of gases to the operation of engines, and remains a cornerstone of modern science. Understanding the evolution of these ideas requires recognizing the contributions of many other scientists who refined and expanded upon the initial discoveries. As researchers delved deeper into the nature of heat and energy, they began to see connections with other areas of physics and chemistry. This interdisciplinary approach led to the development of new theories and technologies, ultimately transforming our understanding of the physical world. In summary, the journey to understanding the principles governing heat and energy was marked by the contributions of several key figures. Carnot's idealized engine and concept of reversibility provided the starting point. Clausius built on this by formalizing the transformation of heat into work and introducing a measure of irreversibility. Kelvin's absolute temperature scale and collaboration with Clausius advanced the field further. Finally, Boltzmann's statistical interpretation of molecular behavior linked microscopic interactions with macroscopic properties, revealing the underlying tendency towards disorder in natural processes. This collaborative effort spanned decades and involved the work of many scientists, each building on the discoveries of their predecessors to develop a coherent and comprehensive theory. Entropy is a concept in science, especially in the fields of thermodynamics and information theory. It is often described as a measure of disorder or randomness. While it might sound complicated, let's break it down in a way that's easy to understand. Imagine you have a brand new deck of cards, all ordered from ace to king in each suit. This ordered deck represents a state of low entropy because everything is neatly organized. Now, if you shuffle the deck, the cards become mixed up and disordered. This shuffled deck represents a state of high entropy because the order is gone. Thermodynamics is the study of heat, energy, and work. One of its key principles is the second law of thermodynamics, which states that in an isolated system, a system with no energy coming in or out, entropy tends to increase over time. This means that things naturally go from order to disorder unless energy is added to create order again. To understand this better, think about your room. If you don't clean it, over time, it gets messier and messier. This messiness is an increase in entropy. To decrease the entropy, you need to put in effort, energy, to clean it up and make it orderly again. A famous physicist, Ludwig Boltzmann, who lived in the 19th century, made significant contributions to our understanding of entropy. He said, "The second law of thermodynamics is the only one that I think will never be overthrown." Boltzmann's work helped us understand that the concept of entropy is linked to the microscopic behavior of particles. Claude Shannon, a mathematician and electrical engineer, extended the concept of entropy to information theory in the mid-20th century. He defined entropy as a measure of uncertainty or information content. In simple terms, if you have a message with lots of possible outcomes, the entropy is high because there's a lot of uncertainty. If the message is very predictable, the entropy is low. For example, if you're guessing the weather and you live in a place where it's almost always sunny, there's low entropy because the outcome is predictable. But if you live in a place with varied weather, there's high entropy because the weather is unpredictable. Think about ice melting. When ice melts, it goes from a structured, solid state, low entropy, to a more disordered liquid state, high entropy. Or consider spraying perfume. When you spray perfume, the molecules spread out from a concentrated area, low entropy, to fill the room, high entropy. Another example is baking a cake. The ingredients start separate and ordered, low entropy. When mixed and baked, they form a cake, which is a more disordered system, higher entropy. While we've learned a lot about entropy, there are still some mysteries. We know that entropy increases over time, but why time flows in one direction, from past to future, is still not fully understood. This is called the arrow of time problem. Black holes have incredibly high entropy, but understanding exactly how and why is still a topic of ongoing research. At the quantum level, where particles behave very differently than they do at larger scales, understanding entropy becomes more complex and is still a major area of study. Entropy is a fascinating concept that touches many aspects of our lives, from the melting of ice to the flow of time. While we have made significant strides in understanding it, there are still many unanswered questions that scientists continue to explore. By learning about entropy, we gain a deeper appreciation of the natural world and the laws that govern it. Expanding on the ideas of entropy, let's dive deeper into its implications and how it affects various aspects of the universe and everyday life. We will explore more examples, historical perspectives, and delve into areas where our understanding of entropy is still evolving. The concept of entropy originated in the field of thermodynamics, which is the study of heat, energy, and their transformations. The second law of thermodynamics, which we mentioned earlier, states that the entropy of an isolated system always increases over time. This law is fundamental to understanding why certain processes occur spontaneously while others do not. Consider a hot cup of coffee left in a room. Over time, the coffee cools down as heat is transferred to the surrounding air. The energy spreads out, leading to an increase in entropy. This process is irreversible. The coffee will not spontaneously heat up again because that would require a decrease in entropy, which contradicts the second law of thermodynamics. One of the earliest scientists to study entropy was Rudolf Clausius, a German physicist in the 19th century. He formulated the concept of entropy to explain why heat flows from hot objects to cold ones and not the other way around. Clausius introduced the term entropy from the Greek word trope, meaning transformation. He famously stated, "The energy of the universe is constant, the entropy of the universe tends to a maximum." Entropy also plays a crucial role in the efficiency of engines and other machines. In any engine, some energy is always lost as waste heat, leading to an increase in entropy. This is why no engine can be 100% efficient. The work of French physicist Sadi Carnot laid the foundation for understanding the limits of engine efficiency. He introduced the concept of a Carnot cycle, which is an idealized engine cycle that defines the maximum possible efficiency an engine can achieve, considering entropy. Beyond thermodynamics, entropy has intriguing applications in information theory, thanks to Claude Shannon. In the context of information, entropy measures the uncertainty or unpredictability of a message. Shannon's groundbreaking work in the mid-20th century laid the foundation for modern digital communication and data compression. For instance, when you zip a file on your computer, the compression algorithm reduces redundancy, effectively lowering the entropy of the data to make the file smaller. Entropy is not just a scientific concept, it also has philosophical and cosmological implications. The idea that the universe tends toward disorder can be unsettling, but it also drives the dynamic processes that shape our world. For example, the mixing of gases, the diffusion of molecules, and the formation of stars and galaxies are all influenced by the principles of entropy. In the context of the universe, entropy is closely related to the concept of the heat death. This is a theoretical scenario in which the universe has reached a state of maximum entropy, with no available energy to do work. In this state, all processes would cease, and the universe would be in thermodynamic equilibrium. While this is a far-off event, billions of years in the future, it highlights the long-term implications of entropy on a cosmic scale. Understanding entropy also sheds light on the nature of time. The increase of entropy provides a direction to time, often referred to as the arrow of time. This concept, introduced by British astronomer Arthur Eddington, suggests that time flows in one direction, from the past to the future, because entropy increases in that direction. This idea helps explain why we remember the past but not the future, and why certain processes, like breaking an egg, are irreversible. Despite our extensive knowledge of entropy, some aspects remain mysterious and are active areas of research. One such area is the relationship between entropy and quantum mechanics. In the quantum realm, particles can exist in multiple states simultaneously, leading to complex behavior that challenges our classical understanding of entropy. Scientists are working to reconcile these differences and develop a more comprehensive theory of entropy that applies to both macroscopic and microscopic scales. Another intriguing area of study is the entropy of black holes. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. In the 1970s, physicist Stephen Hawking discovered that black holes emit radiation, now known as Hawking radiation, due to quantum effects near the event horizon. This radiation implies that black holes have entropy, which is proportional to the area of their event horizon. Understanding the entropy of black holes is crucial for developing a unified theory of physics that combines general relativity and quantum mechanics. In everyday life, we encounter entropy in countless ways. When we mix ingredients while cooking, we increase the system's entropy as the ingredients become more evenly distributed. When we tidy up our rooms, we decrease the entropy locally by organizing our belongings, but we increase the overall entropy of the universe by using energy to clean. Consider the process of diffusion, which occurs when particles spread out from an area of high concentration to an area of low concentration. This process increases entropy because the particles move from a more ordered state to a more disordered state. Diffusion is essential for many natural processes, such as the exchange of oxygen and carbon dioxide in our lungs and the distribution of nutrients in our cells. Entropy also plays a role in the aging process. As we age, the systems in our bodies become less efficient, leading to an increase in entropy. Cells accumulate damage, proteins misfold, and waste products build up, contributing to the overall disorder in our bodies. Understanding how entropy affects biological systems can provide insights into aging and potential ways to mitigate its effects. In the realm of technology, entropy has significant implications for data security and encryption. Cryptography relies on the principles of entropy to create secure communication channels. A high-entropy encryption key is harder to guess or crack because it has more possible combinations, making it more secure. Ensuring that data remains confidential and secure in an increasingly digital world depends on our understanding and application of entropy. Entropy also influences weather and climate patterns. The Earth's atmosphere is a complex system where energy from the sun drives weather phenomena. As solar energy is absorbed and redistributed, it increases the entropy of the atmosphere, leading to the formation of clouds, storms, and other weather events. Understanding these processes helps meteorologists predict weather and climate changes, which is crucial for agriculture, disaster preparedness, and environmental conservation. In summary, entropy is a fundamental concept that permeates many aspects of science and everyday life. It explains why certain processes are irreversible, why disorder tends to increase, and how energy is distributed in systems. From the cooling of coffee to the formation of galaxies, entropy governs the behavior of matter and energy in the universe. While we've made significant strides in understanding entropy, there are still many unanswered questions. The relationship between entropy and time, the behavior of entropy in quantum systems, and the entropy of black holes are just a few areas where our knowledge is still evolving. As scientists continue to explore these mysteries, we will gain a deeper understanding of the natural world and the fundamental laws that govern it. By studying entropy, we not only learn about the principles that drive the universe but also gain insights into practical applications that affect our daily lives. Whether it's improving the efficiency of machines, enhancing data security, or predicting weather patterns, the concept of entropy is integral to advancing technology and improving our understanding of the world around us. To further appreciate entropy, consider the concept of spontaneous processes. These are processes that occur naturally without any external intervention. A classic example is the melting of ice in a warm room. The ice absorbs heat from its surroundings, causing it to melt into water. This process increases the entropy of the system because the structured arrangement of water molecules in the solid ice becomes more disordered in the liquid state. Spontaneous processes are driven by the tendency of systems to move toward states of higher entropy. Another interesting aspect of entropy is its connection to the concept of equilibrium. In a state of equilibrium, a system has reached maximum entropy, and there are no net changes occurring within it. For example, consider a closed container filled with gas. Initially, the gas molecules may be concentrated in one part of the container, but over time, they spread out evenly, reaching a state of maximum entropy. At this point, the system is in equilibrium, and there are no further changes in the distribution of the gas molecules. In chemical reactions, entropy plays a crucial role in determining the direction and extent of the reaction. A reaction will proceed spontaneously if it leads to an increase in the total entropy of the system and its surroundings. This principle is encapsulated in the concept of Gibbs free energy, which combines entropy and enthalpy, a measure of heat content, to predict the spontaneity of a reaction. If the change in Gibbs free energy is negative, the reaction is spontaneous and will proceed without external input. The study of entropy also provides insights into the behavior of complex systems, such as ecosystems and economies. In an ecosystem, energy flows from one trophic level to another, from producers, like plants, to consumers, like herbivores and carnivores. At each step, some energy is lost as heat, increasing the entropy of the system. This loss of energy limits the number of trophic levels and shapes the structure of the ecosystem. Similarly, in an economy, the distribution of resources and energy affects productivity and growth. Understanding the principles of entropy can help economists and ecologists develop more sustainable models for managing resources. Entropy is also a key concept in the field of statistical mechanics, which bridges the gap between macroscopic and microscopic descriptions of matter. Statistical mechanics uses probability theory to describe the behavior of large numbers of particles. By considering all possible microscopic states of a system, scientists can calculate its macroscopic properties, such as temperature, pressure, and entropy. This approach provides a deeper understanding of how the behavior of individual particles leads to the observable properties of matter. In the context of information theory, entropy has profound implications for data transmission and storage. When transmitting data over a communication channel, it is essential to ensure that the message is received accurately and efficiently. Shannon's theory of information entropy quantifies the amount of uncertainty or information content in a message. By reducing redundancy and compressing data, we can transmit information more efficiently, reducing the likelihood of errors and improving the reliability of communication systems. Entropy also influences the design of algorithms and artificial intelligence, AI. In machine learning, entropy is used to measure the randomness or unpredictability of a dataset. Algorithms that minimize entropy can identify patterns and make predictions more accurately. For example, decision trees, a type of machine learning algorithm, use entropy to determine the best way to split data into categories, optimizing the accuracy of predictions. Understanding and applying entropy in AI can lead to more robust and efficient algorithms, enhancing the capabilities of modern technology. In the realm of cosmology, entropy provides insights into the origins and fate of the universe. The Big Bang Theory, which describes the origin of the universe, suggests that the universe began in a state of extremely low entropy. Since then, entropy has been increasing as the universe expands and evolves. The study of cosmic entropy helps scientists understand the large-scale structure of the universe, the formation of galaxies, and the ultimate fate of cosmic objects. One of the most intriguing concepts in cosmology is the idea of the multiverse, which posits the existence of multiple universes, each with its own physical laws and constants. If the multiverse theory is correct, it raises fascinating questions about the nature of entropy in different universes. Do the principles of entropy apply universally, or do they vary across different realities? Exploring these questions could lead to groundbreaking discoveries about the fundamental nature of existence. In the field of thermoelectrics, entropy plays a crucial role in the development of materials that can convert heat into electricity. Thermoelectric materials generate an electric current when there is a temperature difference across them. The efficiency of this conversion depends on the entropy changes within the material. By optimizing the entropy properties of thermoelectric materials, scientists aim to develop more efficient ways to harvest waste heat and convert it into usable energy, contributing to renewable energy technologies and sustainability. Entropy also has implications for the field of medicine, particularly in understanding diseases and developing treatments. Many diseases, such as cancer and neurodegenerative disorders, are associated with increased entropy in biological systems. For example, cancer cells exhibit chaotic and disordered behavior, leading to uncontrolled growth and metastasis. By studying the entropy of cellular processes, researchers can gain insights into the mechanisms of disease and develop targeted therapies to restore order and function. In summary, entropy is a fundamental concept that touches many aspects of science, technology, and everyday life. It explains why processes are irreversible, why disorder tends to increase, and how energy is distributed in systems. From the cooling of coffee to the formation of galaxies, entropy governs the behavior of matter and energy in the universe. While we've made significant strides in understanding entropy, there are still many unanswered questions. The relationship between entropy and time, the behavior of entropy in quantum systems, and the entropy of black holes are just a few areas where our knowledge is still evolving. As scientists continue to explore these mysteries, we will gain a deeper understanding of the natural world and the fundamental laws that govern it. One of the surprising areas where entropy plays a crucial role is in information theory. Information theory is a field of study that deals with how information is measured, transmitted, and processed. In this context, entropy is used to quantify the amount of uncertainty or surprise in a set of information. Scientists are exploring how the concept of entropy can help improve communication systems. For example, they are studying how to encode information more efficiently so that it can be transmitted with fewer errors. Despite significant progress, researchers still don't fully understand how to perfectly balance efficiency and reliability in complex communication systems. In the realm of quantum mechanics, information behaves differently than in classical systems. Quantum information theory is a field that studies how information is processed and transmitted in quantum systems. One of the mysteries here is how entropy behaves in these quantum systems. Researchers are investigating how quantum entanglement, when particles become interconnected in such a way that the state of one can instantly affect the state of another, affects entropy. Black holes are regions in space where gravity is so strong that not even light can escape from them. They are some of the most fascinating and mysterious objects in the universe. Entropy plays a significant role in understanding black holes, but there are still many unanswered questions. One of the major puzzles in black hole physics is the information paradox. According to the theory, information about the matter that falls into a black hole should be lost forever. However, this contradicts the principles of quantum mechanics, which suggest that information cannot be destroyed. Scientists are still trying to resolve this paradox and understand how entropy behaves in this extreme environment. Stephen Hawking proposed that black holes can emit radiation, now known as Hawking radiation, due to quantum effects near the event horizon, the boundary of a black hole. This radiation causes black holes to lose mass and potentially evaporate over time. Researchers are exploring how this radiation affects the entropy of black holes and whether it can provide clues about the ultimate fate of black holes. Entropy is not just a concept for physical systems, it also plays a role in living organisms. Biological systems are incredibly complex and can be thought of as collections of many interacting parts. Understanding entropy in this context is challenging, and there are several mysteries to unravel. Scientists are studying how entropy influences the process of evolution. For instance, some researchers are exploring whether entropy helps drive the evolution of complex biological systems or if it plays a role in the stability and adaptation of living organisms. The relationship between entropy and evolution is still not fully understood. Cells are complex systems with many interacting molecules. Researchers are investigating how entropy affects various cellular processes, such as protein folding, gene expression, and metabolism. Despite advances in our understanding, the exact role of entropy in these processes remains an area of active research. Cosmology is the study of the large-scale structure and history of the universe. Entropy is a key concept in cosmology, but there are still many unknowns related to its role in the universe's evolution and structure. Scientists are exploring how entropy behaved during and after the Big Bang. One question is how the universe's initial low-entropy state evolved into the current state, which includes complex structures like galaxies and stars. Dark energy is a mysterious force that is causing the universe to expand at an accelerating rate. Researchers are investigating how entropy might be related to dark energy and whether it could provide insights into the nature of this enigmatic force. Complexity theory is a field of study that looks at how complex systems behave. These systems consist of many parts that interact in intricate ways, leading to emergent behaviors that are not easily predictable. Entropy plays a role in understanding these complex systems, but there are still many unanswered questions. Complex systems often exhibit emergent properties, which are behaviors or patterns that arise from the interactions of the system's parts. Scientists are studying how entropy influences these emergent properties and whether it can help explain why certain patterns or behaviors emerge in complex systems. Self-organization is a process where a system spontaneously develops ordered structures without external guidance. Researchers are exploring how entropy affects self-organization in various systems, including physical, biological, and social systems. The exact relationship between entropy and self-organization is still not fully understood. Entropy is a concept that stretches across many fields of science, and its implications reach beyond just physical systems. It challenges our understanding of order, disorder, and complexity in the universe. As researchers continue to explore the unknowns of entropy, they are also expanding our knowledge of the natural world and our place in it. Some researchers are exploring whether entropy plays a role in consciousness, the state of being aware and able to think. They are investigating how the brain's complex network of neurons might be influenced by entropy and whether understanding this relationship could offer insights into the nature of consciousness itself. Entropy is also being studied in the context of social systems and human behavior. Scientists are examining how concepts of entropy might apply to economics, sociology, and other areas of human interaction. The goal is to understand whether entropy can help explain patterns in social systems and contribute to solutions for complex social challenges. The study of thermodynamic systems continues to evolve, revealing new insights into the fundamental nature of physical processes. In recent years, researchers have made significant strides in understanding the intricate mechanisms that govern the behavior of energy and matter. One of the most exciting areas of exploration involves the intersection of thermodynamics with quantum mechanics, leading to groundbreaking discoveries about the behavior of small systems at the atomic and molecular levels. Advancements in experimental techniques have enabled scientists to observe and manipulate individual particles with unprecedented precision. These techniques, such as optical tweezers and atomic force microscopy, have allowed researchers to explore the thermodynamic behavior of small systems in ways that were previously impossible. By isolating and controlling individual particles, scientists can investigate the microscopic interactions that give rise to macroscopic phenomena. One of the key discoveries in this field involves the concept of quantum coherence. Quantum coherence refers to the ability of particles to exist in multiple states simultaneously, a fundamental principle of quantum mechanics. Researchers have found that quantum coherence can have a profound impact on the thermodynamic behavior of small systems. For instance, it has been observed that quantum coherence can enhance the efficiency of energy transfer processes, such as those occurring in photosynthesis. By maintaining coherence over long timescales, systems can achieve more efficient energy conversion, a finding that has significant implications for the development of new technologies, such as quantum computers and solar energy devices. Another major breakthrough in the understanding of thermodynamic systems involves the study of non-equilibrium processes. Traditional thermodynamics has focused primarily on systems in equilibrium, where the properties of the system do not change over time. However, many natural and artificial processes occur far from equilibrium, making it essential to develop a theoretical framework to describe these systems. Recent research has led to the formulation of new principles and mathematical models to describe the behavior of systems far from equilibrium. One of the central ideas in this area is the concept of fluctuation theorems. Fluctuation theorems provide a quantitative description of the probability of observing fluctuations in thermodynamic quantities, such as work and heat, in small systems. These theorems reveal that the behavior of small systems can deviate significantly from the predictions of classical thermodynamics, particularly when the system is driven far from equilibrium. Experimental studies have confirmed the validity of fluctuation theorems, providing a deeper understanding of the behavior of small systems and opening new avenues for research in non-equilibrium thermodynamics. The interplay between thermodynamics and information theory has also led to exciting discoveries. Information theory, which deals with the quantification and transmission of information, has been found to have deep connections with thermodynamic processes. One of the most intriguing concepts to emerge from this intersection is the idea of information as a physical quantity that can influence the behavior of thermodynamic systems. Researchers have shown that the acquisition, storage, and processing of information can have thermodynamic consequences. For example, the process of measuring a system and gaining information about its state can affect the system's energy and entropy. This realization has led to the development of new theoretical frameworks, such as the field of quantum thermodynamics, which seeks to describe the thermodynamic behavior of systems in terms of information theory principles. A particularly fascinating application of these ideas is found in the study of Maxwell's demon, a thought experiment proposed by James Clerk Maxwell in the 19th century. The thought experiment involves a hypothetical being that can sort particles based on their energy, seemingly violating the second law of thermodynamics. Recent research has shown that when the information processing capabilities of the demon are taken into account, the apparent paradox is resolved. The acquisition and use of information by the demon require energy, ensuring that the second law of thermodynamics is upheld. Advances in the understanding of biological systems have also been informed by these new thermodynamic principles. Living organisms operate far from equilibrium, constantly exchanging energy and matter with their environment. Researchers have applied the principles of non-equilibrium thermodynamics to study processes such as metabolism, cellular respiration, and photosynthesis. These studies have revealed that biological systems have evolved to optimize energy conversion and minimize dissipation, providing insights into the fundamental principles governing life. In addition to biological systems, researchers have explored the implications of these new thermodynamic discoveries for materials science and engineering. The development of materials with tailored properties, such as high thermal conductivity or efficient energy storage, requires a deep understanding of the thermodynamic principles governing these systems. Advances in nanotechnology have enabled the fabrication of materials with precise control over their atomic and molecular structure, allowing researchers to study the thermodynamic behavior of materials at the nanoscale. One area of particular interest is the study of thermoelectric materials, which can convert heat directly into electricity. The efficiency of thermoelectric materials is governed by their ability to maintain a temperature gradient while minimizing thermal conductivity. Recent research has shown that quantum coherence and non-equilibrium thermodynamics can play a crucial role in enhancing the performance of thermoelectric materials. By understanding and harnessing these principles, scientists aim to develop more efficient thermoelectric devices for applications in energy harvesting and waste heat recovery. Another promising area of research involves the study of phase transitions in small systems. Phase transitions, such as the melting of ice or the boiling of water, are well understood in macroscopic systems. However, the behavior of phase transitions in small systems, such as clusters of atoms or molecules, can differ significantly from their macroscopic counterparts. Researchers have used advanced experimental techniques to study phase transitions in small systems, revealing new insights into the underlying mechanisms. One key finding is that the critical behavior of small systems can be influenced by factors such as surface effects and quantum fluctuations. These factors can lead to deviations from classical phase transition behavior, resulting in phenomena such as supercooling and superheating. Understanding these effects is essential for the development of new materials and technologies, particularly in the fields of nanotechnology and condensed matter physics. The study of entropy production in biological systems has also been an area of intense research. Biological systems, such as cells and organisms, operate far from equilibrium and continuously produce entropy as they carry out life processes. Researchers have developed new theoretical frameworks to describe the production of entropy in biological systems, revealing how these systems maintain order and function despite the inherent tendency towards disorder. One important discovery in this field involves the concept of dissipative structures. Dissipative structures are ordered patterns that emerge in systems far from equilibrium due to the flow of energy and matter. Examples of dissipative structures in biological systems include the intricate patterns of cellular organization and the dynamic behavior of metabolic networks. Understanding how dissipative structures form and maintain themselves has provided new insights into the fundamental principles of life and the evolution of complexity. The development of new computational techniques has also played a crucial role in advancing the understanding of thermodynamic systems. High-performance computing and advanced algorithms have enabled researchers to simulate the behavior of complex systems with high accuracy. These simulations provide valuable insights into the microscopic interactions that give rise to macroscopic properties, allowing researchers to test theoretical predictions and explore new phenomena. One area where computational techniques have been particularly valuable is in the study of molecular motors. Molecular motors are protein complexes that convert chemical energy into mechanical work, playing a crucial role in cellular processes such as transport and division. Researchers have used computational simulations to study the behavior of molecular motors, revealing how they achieve high efficiency and specificity in their functions. These studies have provided valuable insights into the design principles of biological nanomachines and have potential applications in the development of synthetic molecular devices. The exploration of the connections between thermodynamics and gravity has also led to exciting new discoveries. Researchers have proposed that the laws of thermodynamics may have deep connections with the fundamental nature of space and time. One particularly intriguing idea is the holographic principle, which suggests that the information content of a region of space can be encoded on its boundary. This principle has profound implications for the understanding of black holes and the nature of the universe. In recent years, researchers have made significant progress in understanding the thermodynamic properties of black holes. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. Despite their extreme nature, black holes obey the laws of thermodynamics, with properties such as temperature and entropy. The study of black hole thermodynamics has revealed deep connections between gravity, quantum mechanics, and information theory, providing new insights into the fundamental nature of the universe. One of the most important discoveries in this field is the realization that black holes emit radiation, a phenomenon known as Hawking radiation. Hawking radiation arises from quantum effects near the event horizon of a black hole and leads to the gradual evaporation of the black hole over time. This discovery has profound implications for the understanding of black holes and the nature of space and time, suggesting that the laws of thermodynamics apply even in the most extreme conditions. The study of the thermodynamic behavior of small systems has also led to new insights into the nature of time. In macroscopic systems, the direction of time is often associated with the increase in disorder or randomness. However, the behavior of small systems can exhibit time-symmetric properties, where processes can occur in both forward and reverse directions with equal probability. Researchers have investigated the implications of these findings for the understanding of the arrow of time, leading to new theoretical frameworks that describe the behavior of time in small systems. One key concept in this area is the idea of time reversal symmetry breaking. Time reversal symmetry breaking occurs when the behavior of a system changes depending on the direction of time. Researchers have shown that in small systems, time reversal symmetry breaking can arise from factors such as quantum fluctuations and the exchange of information. Understanding these effects is essential for developing a comprehensive theory of time that applies to both macroscopic and microscopic systems. The study of thermodynamic systems continues to evolve, revealing new insights into the fundamental nature of physical processes. Advances in experimental techniques, theoretical frameworks, and computational methods have enabled researchers to explore the behavior of small systems with unprecedented precision. These discoveries have profound implications for a wide range of fields, from quantum mechanics and information theory to biology and materials science. As researchers continue to investigate the intricate mechanisms that govern the behavior of energy and matter, they are uncovering new principles that deepen our understanding of the physical world and pave the way for the development of new technologies. By studying entropy, we not only learn about the principles that drive the universe but also gain insights into practical applications that affect our daily lives. Whether it's improving the efficiency of machines, enhancing data security, or predicting weather patterns, the concept of entropy is integral to advancing technology and improving our understanding of the world around us. The concept of entropy also highlights the importance of sustainability and resource management. In a world with finite resources, understanding how to manage entropy can help us develop more sustainable practices. For example, reducing waste, recycling materials, and using renewable energy sources are all ways to manage entropy and minimize our impact on the environment. By considering the principles of entropy, we can make more informed decisions about how to use and conserve resources for future generations. If you know anything else interesting about entropy, please let us know in the comments. Thank you for watching Mysterious Nuggets. Please like and subscribe for more content.